Pre-Calc PLP. So this is lesson 2. This is over radicals and rational exponents. So at the beginning of this lesson, there is this table that is a review of exponential properties. These should all be a review. I really would like you guys to look over these before you start this lesson and make sure you remember them. We're going to start off with a little bit of review. We're going to practice simplifying radicals. Now, to do these examples, we don't necessarily have to switch to rational exponents yet. We're just going to simplify. These are all square roots. So, when you are simplifying square roots, I always do the factor tree method. Remember, you're looking for pairs or perfect squares that you could take out from under the radical. So let's take that 27 and simplify it down with a factor tree to see if there's any perfect squares. So I know that 9 times 3 is 27, and 9 is going to be the perfect square that I could take out. We're looking for pairs. Since 9 is 3 times 3, that means I can take the square root of 9, and the 3 gets to come out, so I have -2, and then I'm going to have a 3 out here. Now that other 3 kind of gets stuck underneath. Let's talk about the x to the 5th now. Again, I am looking for pairs. So we can take the square root of part of x to the 5th. Think about how many groups of 2 you can take out of x to the 5th. I can take out 2 groups of 2. So I'm going to put x squared on the outside. And if I take out 2 groups of 2, that's kind of like taking 4 of them out. So there's 1 left underneath. So underneath the radical, I have that leftover 3 from my 27, but I'm also going to have 1 leftover x because we took the square root of x to the 4th, which was x squared, with 1 left over. So let's move on over to the other one. Now this other section we can actually do nothing with. I cannot take the square roots of 3 or x, so that's just going to stay. Now there's one other thing that I can do here. So if you guys notice, both of these have this x squared square root of 3x. So these are like terms. Now on the first one, I technically have a -6 over there from my -2 times 3. And then the second term, I have a -1. -6 minus 1, if I combine my like terms, would be -7. So I can actually combine these and say -7 x squared square root of 3x. And there would be my final answer, completely simplified. So let's do this next one. Start over here. We're taking a square root, so we're looking for pairs of numbers. 48 is 16 times 3. You could pick other numbers if you want, but I chose 16 because I know that it's a perfect square. So that means I can take the square root here. Square root of 16 is 4, so that 4 gets to come out. I'm going to put that up by the 2. X. Now let's think about x cubed, x to the 3rd power. Think about how many groups of 2 you could take out. I can take the square root of x squared, or I can take one group of 2, so there would be one x on the outside, but I'd have another x on the inside, along with my 3 from my 48. Okay, let's move over here. I'll simplify that in just a second. Now over here, I cannot take the square root of my 3. However, I can simplify the square root of x to the 5th just a little bit, just like we did on the last example. Think about how many groups of 2 you could take out from x to the 5th power. The answer to that question would be 2 groups of 2. Or you could think of it as you can take the square root of x to the 4th, which would be x squared. However, there would be 1 left over, so you would have 3x. So I'm going to clean this up just a little bit. So over here we would have 8x squared, square root of 3x. Over here we'd have 9x squared, square root of 3x. So again, I can combine these. Think of these like terms. So I have 8 on the left, 9 on the right. I can add those together, and I can say that it is 17 square root of 3x. There you go. And number 3. I have 3 over 2 plus the square root of 14. Now, we have to rationalize this denominator. You cannot have a square root in the denominator. So, to get rid of this, I have to multiply by the conjugate. If you forgot what a conjugate is, it looks kind of like this. So the conjugate of 2 plus square root of 14 would be 2 minus square root of 14. And the reason we do this is because when you multiply by the conjugate, it's going to cancel out the 2 middle terms, and it's also going to eliminate your square root. So I'm going to do the top first. The top is pretty simple. I'm going to take my 3. I ran out of room there, but I'm going to take my 3 and I'm going to distribute it to these two. So I would have 6 minus 3 square root 14. Now on the bottom, I'm going to think of this like foiling. Or you could use box method, but I need to take 2 plus square root of 14 times 2 minus square root of 14. And I'm going to write this all out so you can see how the middle terms will cancel. My first terms are 2 times 2, which is 4. And then I have 2 times negative square root of 14, which is 2 root 14. And then I have 2 times positive square root of 14 on the inside. And that's where those terms are canceling out. And then my last 2 terms, I would have square root of 14 times negative square root of 14, which is a negative 14. So let's just clean this up. On the top, I have 6 minus 3 square root 14. On the bottom, these 2 middle terms are gone, so I'm just left with 4 minus 14, which is negative 10. I can leave it at that. Okay. Moving on. So let's talk about rational exponents. If a is a real number and n is a positive integer, such that the principal nth root of a exists, then a to the 1 over n power is defined as the nth root of a. So basically you can rewrite a rational exponent as a radical. So for example, if I had x to the 1/2 power, that's the same thing as the square root of x. If I had x to the 1/3 power, that's the same thing as the cube root of x. Pretty simple. Or vice versa. If m is a positive integer, then a to the m over n power is a to the nth root, and I'd have m as my power. Okay. So we're going to simplify these. Number 1, I have 7x to the negative 5/2. Be very careful here. The 7x is not in parentheses, so that means if I don't have parentheses, that negative 1/5 power, 5/2 power, only belongs to the x, not to the 7. So if you read your exponent rules up at the top, you would have read that if you have a negative exponent, you write the reciprocal. So that x to the negative 5/2 power gets to go to the basement, or the denominator. So I'd have 7 on top, because it does not have the power. And then my x would go to the bottom, but I'm going to rewrite it as a radical, and I'm going to write square root, I don't need to write the 2, x to the 5th. Okay. Now the problem with this is we need to rationalize the denominator. We can also simplify something a little bit here. I'm going to go ahead and take or simplify the square root of x to the 5th. I can take out 2 groups of 2, so it'll be x squared, square root of x. To rationalize the denominator, I'm going to multiply top and bottom by square root of x to get that square root out of the bottom. So I would have 7 square root x over x cubed, because the square root of x times the square root of x is just x, times x squared is x cubed. So there's my answer. So let's do this one. Kind of a similar pattern to the last one. I'm going to move my exponent to the bottom since it's negative. Then I'm going to rewrite it as a square root. So I would have square root of x cubed, which I can take out one pair of 2. So I'd have x, and then 1x would be left over. Now I'm going to rationalize the denominator. I'm running out of room. To rationalize the denominator, I'll multiply by the square root of x. And I'm going to move that down here. So I'd have 3 square root of x. And then I have square root of x times square root of x on the bottom, which is x, times another x is x squared. There's that. Now this one is a little bit different. We do not have a variable now. We are just going to simplify this. I'm going to rewrite this as a 5th root because I have a 1/5 power. And I'm going to go ahead and do 4 cubed. 4 cubed is 64. And we're going to see if we can simplify this. So we're going to break this down using a factor tree. Now remember, if we're using a 5th root, we're going to look for groups of 5 when we do this. So I'm going to start breaking it down. I'm going to do 32 times 2. Okay, so there's one prime number. 16 times 2. There's another. 4 times 4. 2, 2, 2, 2. So if you guys notice, there is a group of 5 that I can take out. I'm going to highlight 1, 2, 3, 4, 5. I could take the 5th root of all of those. So I have one group of 5 coming out. And notice there was only one left over, so this becomes 2 root 2. Okay. Now number 4, I really like number 4, because if you notice, we have 2 radicals, but they're both to a different root or a different degree. So the first one is the 4th root, second one is the cube root. There's actually a way that you could combine these into one common radical. So I'm going to try to clean it up a little bit first, because you can actually take the 4th root of 16. The 4th root of 16 is actually just 2, so I'm just going to do that. But I'm going to leave my 4th root of x squared under there. And then I can actually take the cube root of 64 as well, which I believe is 6. No, that's not right. 4. I knew that. 4. But I'm going to leave my x underneath because I cannot take the cube root of an x. Okay, I'm going to put my 2 times 4 out the front. So this is what I have right now. I'm going to rewrite these as an exponential now, or as rational exponents. So I'm going to have x 2 over 4 times x to the 1/3. Now, both of those have a base of x. So according to your exponent rules, I'm going to scroll up just to remind you guys, because it is up here. If you're multiplying 2 of the same base, then you add your exponents. We can do that here, but we are adding fractions. So we're going to take 2 over 4 plus 1/3 off to the side. Just remember, if you're going to add these together, you have to have a common denominator. That's how we add fractions. So my common denominator here would be 12. So I would have 6 over 12, which is the same thing as 2 over 4, plus 4 over 12 equals 10 over 12. And I'm going to reduce that, which is 5/6. So basically, if I took x to the 2/4 times x to the 1/3, I'm going to get x to the 5 over 6, and then I can rewrite it as a radical. So I have my 8 out at front, which means I'm going to have a 6th root, x to the 5th. There you go. And next one, similar situation. You have an x to the 6th that's under a cube root, and then you have a square root. Let's simplify it first. Sometimes it'll simplify all the way, so let's check this out. You can actually take the cube root of 216, and that is 6. And you can take the cube root of x to the 6th as well, because if you think about a cube root and x to the 6th, we're looking for how many groups of 3 can we take out. We can take out 2 groups of 3, and there would be nothing left over under that radical. So that one simplifies completely. Now look at the next one. It's a square root. We know we can take the square root of 49, which is 7. You can also take the square root of x to the 4th, or think of it, how many groups of 2 can I take out? I can take out 2 groups of 2 with none left over. The square root of x to the 4th is x squared. So that one simplifies completely, and we can actually multiply those together. So I'd have 42, and then x squared times x squared is x to the 4th. So that one's nice and pretty. So pause the video. This is time for your independent practice. When you are done, you can unpause the video and check my solutions. So if you're done, here they are. And if you have any questions at all, please don't hesitate to reach out. Make sure you guys are doing your practice. And I hope you have a wonderful day.